Hello there, everyone. This is Mrs. Hanson, and we begin our journey in the next chapter, chapter 11, simply titled Synthesis. Looking at our strategy, we can see the sections that we need to discuss together. One-step synthesis, followed by the functional group transformations and then reactions that change the carbon skeleton. This will be the focus of the first lesson. And then I'll pick up a second video on how to approach a synthesis problem, retrosynthetic analysis, just working backwards, and practical tips to increase your proficiency. And I must say, there is absolutely no new chemistry introduced in this chapter. It's really just an application of everything we've learned so far. This is the culmination of all of the hard work you've been putting into the class and making us kind of remember and how to apply it in a synthesis reaction. This is a chapter that I cannot stress enough that practice will lead to proficiency. This is not a spectator sport. The more problems you work, the more patterns you become familiar with, and the quicker and more proficient you become. So I can't encourage you enough to just practice with your synthesis chapter. So before we begin, I'm going to just highlight what I believe to be the most critical sections in terms of reviewing and laying a strong foundation for this particular chapter. So substitution versus elimination in section 7.11. You want to find your notes in that particular section, and I'll highlight some of those major, each one of these sections, I'm going to highlight some of those topics. Then I need to go back and look at 8.14 for alkene synthesis and 9.11 for alkyne synthesis. Looking at strategies for substitution versus elimination, back to 7.13. And then the last 10.13 using a halogenation as a synthetic technique. Specifically, if you see Br2 on an arrow with H nu for energy, what would that look like in a synthesis? So this is a wonderful practice opportunity to go back and dive in and kind of begin firming up those sections as we begin to apply the tools, the reagents we've been working with in a synthesis chapter. In the introduction in your ebook, there is a chapter practice there that gives you some practice problems. It might just be a great place to start in bringing back some of those reagent tools from previous chapters. So I mentioned that these sections that I highlighted, I'm going to just go through very quickly each one and make you kind of pull out your notes or get thinking about the following. So for instance, 7.11, this is how we were kind of leaving that chapter 7 and predicting products. How do I know if it's substitution versus elimination? And we discussed that there are some steps to go through to decide what type of reaction will occur. And sometimes there's competing reactions and you have both products to consider. So the first step in determining if it's substitution versus elimination, we want to determine the function of the reagent. So notice that substitution occurs when the reagent functions as a nucleophile. If I have a strong nucleophile, I'm encouraging substitution. Elimination occurs when the reagent functions as a base. And so we're looking for those that would be strong bases. And you can clearly see there's some overlap with both are considered strong. The second item that we were told to consider to determine if it's substitution or elimination is looking at the substrate. Remember, the substrate is the alkyl that has the halogen on it, right? And so it contains the leaving group. And so we're looking at, looking to decide what type of substrate. Is it a primary substrate, a secondary substrate, or a tertiary substrate? Versus these categories we talked about up here, strong base, weak base, strong nucleophile, or weak nucleophile. And this is a critical graph to let us decide what is being favored, an E2 mechanism or an SN2 mechanism, or down here we have a little bit of SN1 and a tiny box of E1 with a weak base and a tertiary substrate. But again, this is a 50-50 mixture, very much a competing reaction. So keep in mind that particular box and see the need to memorize these we have to understand where those fall as we decide what type of mechanism we'd like to employ. So with a strong base, a primary substrate, you're going to see a major SN2 reaction. If you have a secondary substrate, a major E2 with a strong base, and a tertiary substrate with a strong base, you only get E2. And so put that together. We just said strong base, a strong base in a nucleophile. We're looking at a combination for a primary, a little bit less of that with a secondary, and 100% with a tertiary E2. So again, just consider thinking about how I can what kind of products am I going to get out based on what's sitting on the arrow and what type of substrate that we have. And you want to consider any relevant regiochemical or stereochemical requirements, and just thinking about SN2 reactions with its regiochemical outcome, thinking about the alpha position where the leaving group is connected, so that bimolecular collision forces the leaving group to leave from that alpha carbon. And then the nucleophile replaces the leaving group with 100% inversion. Remember, we called that the backdoor attack. In an E2 mechanism, the Zaitsev product is generally favored over the Hofmann product. What that means is that you're going to create the double bond between the most substituted carbons, and the Hofmann puts the double bond at the least substituted carbon. Unless the sterically hindered base is used, and that's that big bulky base in which the Hofmann product is favored simply due to steric hindrance. Something to consider there is the trans disubstituted alkene will be favored over cis just due to stability. And it's also stereospecific at the beta position of the substrate because there's just one proton there. So remember that we had an anti-periplanar elimination, especially in that cyclic structure. So if you're thinking about a cyclic structure and this bromine is pointing down, it has to be a pointing up proton to be eliminated. That would be too far away. Right here is where I meant to draw that. So again, just thinking about where is the hydrogen available in being very specific to the beta substrate. SN1 and E1 typically aren't used so much in our chapters coming up here in synthesis, but it's a good review. Remember that there's a carbocation intermediate in an SN1. That means it's a nucleophilic unimolecular first step, and that's where the leaving group just leaves. And so that's the rate determining step. And when the leaving group leaves, the carbocation is created, and look for rearrangements as a possibility. And in the E1, the Zaitsev is always favored over the Hofmann product, again, due to the most substituted carbon is going to create on that positive charge there in the carbocation. So again, just a nice review of that section, but man, is it important to just have this down solid, because we don't stand a chance of creating a correct synthesis if I don't understand the tools I'm given to create. The next section I wanted to highlight with you to go back and just really put some focus in on is 7.13, and this is the chapter for synthesis strategies, substitution and elimination reactions. And this is just a opportunity to kind of review if I'm starting with a primary substrate. So just an opportunity to say, here we're starting with an alkyl halide in a primary position. So that carbon that's attached to the bromine is attached to just one other carbon. And we can see that if we have, for instance, the cyanide, CN, C triple bond N, the substitution here that will take place turns the bromine into a nitrile. Remember, the sodium is just a spectator, so it's just going to travel along to keep it electrically neutral. If we have a primary alkyl halide and we add a COO negative, remember this is originally from the carboxylic acid, so it's a carboxylate ion, negative ion, and it's going to add across to create the ester. So notice that's the COO linkage, the ester linkage. Here's the original carbon. Here's the COO ester linkage, and you add on to the original alkyl halide. Here's a thio group, SH negative. The SH negative, here the thiol, think sulfur. And again, the bromine is going to be substituted for that SH group. So if you need to add sulfur across the bond, this substitution reaction will work well. Here is OCH negative. OCH negative, remember the leaving group leaves, and OCH3 would add on, and you end up creating an ether. Here is a big, bulky base, or a very strong base like hydride with a primary alkyl halide. You're going to form an alkene. With a strong base such as hydroxide, OH negative, you can convert it into a primary alcohol. And the last, you're thinking of other directions we can go. If we're starting with an alcohol as our primary substrate, not this, we were just going through all the different ways we could do a bromide, but if we started with an alcohol, let's remember that an alcohol is a horrible leaving group. And one of the first steps you always undergo is if you're trying to remove an alcohol, you have to make it a better leaving group, and you do so with a tosylate. So you end up taking the OH and converting it to an OTS, a tosylate compound. And see this? This is TSCl, tosylate chloride, in pyridine. And you've removed the hydrogen and added on the tosylate, and you turn that into a better leaving group so that the leaving group leaves, and we can create the alkene. With a big bulky base, we can convert that into an alkene from position carbon 1 to carbon 2. This can actually go back to the alcohol by treating it with base. The primary alcohol can be converted into a primary halide just by adding HBr. Again, going through all those different mechanisms with primaries, and then tell yourself, well, I better practice at the other end as well. What can I do with tertiary? These are all examples of tertiary substrates. So here's a tertiary alcohol. Here's a tertiary halide. And what we're trying to remember is all those tricks we can do to convert one to the other. A tertiary alcohol, if it's going to be a leaving group, must be treated with a tosylate compound to turn this into a better leaving group. When the leaving group leaves, OTS negative, remember hydroxide is a poor leaving group because it can't stabilize the negative charge on such a small oxygen. So what we do is create a larger surface area for it to stabilize the negative charge by adding that tosylate compound to it. So if an alcohol is being used, always treat it with the tosylate chloride in a pyridine workup, and then you created then a better leaving group. Hit it with a big bulky base and you get a Hoffman alkene. Treat it with a strong base and you'll get a Zaitsev alkene. Take that alcohol and use an acid catalyzed dehydration and you'll get an alkene Zaitsev. Same thing with an alkyl halide that's tertiary. Treat it with a strong base and you'll form a Zaitsev. Treat it with a big bulky base and you end up with the Hoffman product. Just stressing, this was review, but these are the critical building blocks we'll be using in this current chapter. Let's go on and take a peek at 9.11, synthesis strategies. Here's chapter 9 was alkynes. And so we're kind of going back and putting in some ideas of what's going across pi bonds. If we start with a triple bond, and we remember treating it with hydrogen across a metal platinum or metal catalyst like platinum or nickel would work, palladium works, but it's a surface chemistry. And so remember, it's the same side addition. But if we're going all the way to an alkane, there's really no way to stop it at the alkene. It will saturate every pi bond. Remember Lindlar's catalyst, we called it a poison catalyst, and this was going to create a cis configuration of the alkene. Or you could use elemental sodium in a workup of ammonia and get a trans alkene, and then that stops You don't go all the way to the ane. Here is an ene, a double bond, treated in a boring solvent, carbon tetrachloride, which is nonpolar, and you're going to add the bromine across the double bond in the trans position here. And then remember, if you treat this with sodium amide, just remember this amide, that NH2 negative, is going to come across here and kind of attack this carbon, because that carbon is positively charged just based on the polarity of the bond. Remember, this is an electron withdrawing group. So this carbon is going to be the electrophilic center, and the leaving group leaves. And remember, what you're doing there is just kind of creating ultimately that triple bond that had a pair of electrons and a negative charge. It says excess amount, so that you do that again to the other side. And at the other side, you're left with another negative charge. And the workup with water afterwards, that water treatment says, well, we're going to be able to reprotonate and add hydrogens to the terminal end, so that those terminal hydrogens are present instead of the negative charge. And then finally, as we're looking down here, some other interesting things we were doing, working up with hydrogen. Remember, we had kind of said, see chapter 10, how do I change an ane into an ene? Well, now that we've covered chapter 10, we understand this is a radical mechanism. And so that is one of those the six radical mechanisms that we work to memorize from our chapter 10. Changing an ane to an ene as a radical initiation, propagation, and termination step. In 8.14, we also worked up with synthesis strategies. And just some basic things to keep in mind. Substitution reactions are when we convert one group into another. If I want to change an alcohol into a bromine, if I want to change a chlorine into a alcohol, whatever it might be, I'm converting functional groups. Elimination reactions eliminate the halogen or the alcohol. We're removing something, and notice how an ane turned to an ene. So we're creating a pi bond through elimination. And those addition reactions are characterized by two groups adding across a double bond. Here is an alkene. We can see that it's a 4-carbon alkene, so this would be 2-butene. And I'm adding across XY, whatever X might be, could be something like HCl, could be ClCl. There's a lot of choice what that might be. But each carbon then creates a new bond, and we end up with sp3 hybridization. So just adding across the double bond. Also, we have to keep in mind that sometimes we can change the position of the leaving group. And that's very kind of one of the first things we do is look at what we're starting with and look at the target molecule we're trying to make and decide, did the functional groups change? Did they change position, or are they on the same carbon? And this is a very common synthesis plan where the first step is an elimination reaction and the second step is the addition reaction. So for instance, here I have a carbon chain that is 4 carbons long. At carbon number 2 is a bromine. At carbon number 3 is a methyl. And the desired product at the very end, I still have a 4-carbon chain. And that 4-carbon chain, it still has the methyl in the same position, but the bromo has changed. Bromine went from carbon position 2 to carbon position 3. So we ask ourselves, how do we just move a bromine across from one carbon to the next? And that answer lies in a 2-step process. We first perform an elimination reaction, and the elimination reaction creates this double bond. Then we can add back across the double bond, and notice that the bromine attached to the carbon that has the most carbon, and so therefore we would call that a Markovnikov addition. In this particular process, an elimination occurs. You want to be careful about deciding, would we like it to be Zaitsev or would we like it to be Hofmann? And knowing that we want the double bond ultimately to add the bromine here, it makes sense that we want the Zaitsev double bond to form. We don't want the bromine to end up on carbon 1, we want it to end up on carbon 3. So a careful selection of the elimination reagent will determine where the double bond forms. We want a strong base to favor the Zaitsev elimination. If we had selected a big bulky base on this secondary alkyl halide, we would have gotten the least substituted double bond to form, the Hofmann product. So that's another consideration as we're working towards deciding what type of reagent. We have to think about where do we want the double bond to end. One last time to kind of focus, if I'm looking at an alcohol, I want to say this once more, you will always need this step prior to doing any of the other manipulations, and that step is converting the alcohol, which is a bad leaving group, into a good leaving group, and the tosylate compound will do that for us. So here we have a tertiary. Notice its carbon is attached to 3 other carbons, so it's a tertiary alkyl halide with a big bulky base. So we'll have the Hofmann elimination occur, where the carbon to carbon double bond forms with the least substituted area. And then notice here in this addition step, BH3THF, I think of boron in peroxide, and that in our reagent toolbox we know is an anti-Markovnikov, and we have seen that in chapter 8 in the enes, and we also saw that in chapter 9 with the ines. Anti-Markovnikov addition, so we see that the double bond has now been, we've removed the OH and put it on to the primary position. So again, the ultimate goal, the original hydroxyl group OH was at position number 1, 2, 3 in this 5-carbon chain. Through this synthesis, it ended up to be on this particular carbon down here at the original methyl. So we moved it from position 3 on the major backbone down to this carbon, which was the original methyl. And we have to strategize. That's the goal of our new chapter, is to strategize how do we turn this compound, the reactant we're given, into the desired product, and think about all the steps that we have to put together to get from one place to the next. So let's begin. That was all just kind of emphasizing, boy, it would be a really good time to commit to memory your tools and reagents as we begin our one-step synthesis and turn it into a multi-step synthesis, the goal of our chapter. So the most straightforward synthesis problems, the ones that really require drill work, are the one-step synthesis. Because if I'm working through a multi-step synthesis, I must have my working vocabulary to pick from for the multiple steps to put together. I took a screenshot and put this in here from our e-text, and this would be kind of an excellent sit down and focus and put this to memory, build some flashcards if needed, but I need to memorize this particular, with everything I keep saying, you need to memorize. But in all of these slides, it's to your advantage to figure out what tools, and the tools sit on top of the arrow. Here is a cyclohexene. At carbon number 1, we have a methyl group. And I need to know what each one of these tools on every one of these arrows has the ability to do to convert the cyclohexene, methyl cyclohexene, into the desired product. And you can see where I can find those products or these tools down here. And we can go through those, but this is review. I've already taught the lessons on how these worked in the previous chapters. It's now time to just really sit down and memorize these. I've used flashcards when I was a student. Sometimes, better is if you have a more photogenic memory, you can just sit there and commit this to memory. But whatever works for you, it's going to take time to do it. So start committing the time. Just to kind of think about all of these tools, you might consider printing that in your e-learning. I put a document together that placed all of those important tools in a series of pages, and you might find that easy to memorize that way as well. So look in your e-learning for that document, and all that document is kind of screenshots of the slides I presented, and that way you can have them all in one spot as you work to commit those to memory. So let's just kind of practice, and you have that, your toolbox in place. Which one of these sets of conditions would accomplish the following transformation in a high yield? So we're asking you, what do we put on the arrow? How do we get from this spot to this spot, the left side to the right side, the reactant to the product, if you will? So let's kind of just begin by focusing here. I see that I have an alkyl 5-carbon chain, and at carbon number 2 we have a hydroxy group. Now I notice that the position of the function didn't change. Carbon 2 still is the location for the functional group, but the identity of the functional group has changed. It converts from an alcohol into an azide, N3. So we're being asked to try to figure out what would do this transformation. One thing I wanted to emphasize in this multiple choice setting especially, and I've said it in this workup many times, what's the first thing you need to do before a leaving group of hydroxyl will leave? And remember, that's what the ultimate plan is. You have to do addition, elimination. Those are your types of reactions to choose from. And if I'm looking through on this series, I immediately go to this guy because I have to change the alcohol into a leaving group that's a better leaving group. And we do so by putting a tosylate compound on them. And then we could see that N3, and again, that's a negative. The sodium is just a spectator. In a workup of a nonpolar solvent of DMSO, this would be a bimolecular backdoor attack. And so therefore, we'll have an inversion, right? 100% inversion, because the molecule itself, in a bimolecular collision, the leaving group leaves when it's attacked from the back door. So we can see the inversion occur through that SN2 mechanism. And I know my answer just is correct because the tosylate gave that away, that I have to convert the alcohol into the tosylate. Then I can add the sodium azide into the DMSO workup. How about another? Again, trying to practice some, some multiple choice, because that's how the test will look. And it's just good practice to kind of do not only drawing, but look at this type of problem as well. Choose the expected product from the following reaction. So again, once I get very familiar with my reagents, call them your tools in your toolbox, and we can begin to understand what will happen. I have 5 carbons in that chain. And at carbon number 2, we have a hydroxyl group, and it's in a dash position. We understand the first step is simply changing the hydroxyl group into a better leaving group by adding tosylate compound to it. So that's all that first step does. And in the second step, we see that we have cyanide, which is the negative compound here, CN negative. CN negative, and sodium is the plus. So therefore, we can predict that a cyanide is going to add across where we see the OTS. And keep in mind, if this is a SN2 bimolecular collision, we will have an inversion of the compound. So which one matches that slide? When we look at the dash to the wedge, I highlighted here. How are you doing? Let's try another. Which of the following nucleophiles is required for the transformation below? Alrighty, so let's figure out what we have. Here I'm given this tosylate so that we can see that this came from an alcohol originally, but I've made it into a better leaving group. So I'm kind of starting at the next step of this workup. And the tosylate compound has turned into a thio group that contains 2 carbons in addition. So I could see a CH3, CH2, SH is kind of the original molecule. What we want to look at is the compound that's going to do that and add just the right number of carbons. So here's carbon 1, carbon 2, carbon 1, carbon 2, but that's an oxygen. We want it to be a sulfur. That has too many carbons. That has too many carbons. This CCS negative, K positive, so instead of a hydrogen, we're just neutralizing the charge with the potassium. That's going to be the workup to give us our, the interconversion of one functional group to the next. So see how we're just using a little logic to decide what did we start with, where are we going? Let's try another, because, repetition's our friend while we're learning. Here's another one we're asked, which of the following reagents will most likely give us E2 product as a major outcome with a secondary alkyl halide substrate? So I put these on here from a previous slide, and you're committing them to memory. Here is the secondary alkyl halide, and we want to know where is the E2 being favored. What types of things can go into E2 as a mechanism? And I can see both choices are going to work here. Strong base, weak nucleophile, or strong base, strong nucleophile. And again, I emphasized in the previous slide, we've got to work to memory what those mean. Strong base, strong nucleophile, strong base, weak nucleophile, and then go up in here and decide which ones match. Do you see any? Here we have a primary carbon, so think of that as an RO negative, and that's going to fit right into this category here as a strong base, strong nucleophile. And even here I have, even though this is a big bulky base, it still has an oxide, and the oxides we're seeing in this general area as being strong. So these two will work. Bromide, here's bromide, and I can see that falls into the weak category. And here we have the sulfur compound, and that's falling into the weak category. So those will not work. So of our choices, the first two will promote an E2 as a major outcome, but not the other two choices. Same idea, and I recaptured those images because you're working to remember them. Which of those substrates will give E2 as a major outcome with OCH3 negative? OCH3 negative is MEO, right? That's a methoxide anion. So if a strong base, strong nucleophile, that's this particular column, and we want E2 as the major product, it can be a secondary or a tertiary alkyl halide, but not the primary. SN2 would be the dominant reactant there. So here I can recognize this is a carbon attached to 3 other carbon and a bromine. That is a tertiary alkyl halide. Here's a carbon attached to 2 other carbons and a bromine, and this would be your primary. So just kind of picking apart that molecule, and you can find the 2 that worked as being secondary or tertiary is what we were hunting for. There's 2 of the 4 choices that we select. So right now, all I've done in section 1 of chapter 11 is told you everything you should review, everything you should commit to memory, and then it would be a really good time to just look at your checkpoint 1 and 2 in your Wiley homework, because those are those one-step synthesis reactions, and it may help you as you work to commit those to memory. It'd be a good idea to give them a try right now. Pause the video, come back, and start up with section 2 once you have a good handle on the review so far. In the second section, functional group transformations. So we begin to apply the fundamentals presented in the review section of the first, 11.1. We're going to apply that as we begin synthesis strategies. So let's review a two-step synthesis, and these will get up to 5, 6, 7, 8 steps as we get better and better at these. Let's begin with a fundamental two-step synthesis. And I said the most common is an elimination followed by an addition. Here we have a secondary alkyl halide. This would be 1, 2, 3, 4 carbons long. And we're converting that into a tertiary alkyl halide. So think of this kind of as your given substrate, and here is what you want to convert it into. An essential question here is, how do we move a bromine from carbon 2 to carbon 3? Because that's exactly what we've done. And the answer to that lies in an elimination to create a double bond, followed by addition of HBr. So we want to eliminate HBr, and we're going to add it back on in the next step. Notice that we have to carefully select the reagent to produce a Zaitsev most substituted alkene. So we need to choose a strong base, and the strong base we want to eliminate from the secondary alkyl halide to create Zaitsev. And then notice that we want an Markovnikov addition where the bromine adds on to the most substituted carbon. So these are two considerations as we select our reagents. It would be a completely different story if we had wanted to add the bromine, over here to the first carbon. That's a completely different process where we would then want a Hofmann elimination followed by an anti-Markovnikov addition. So just kind of getting our wheels set of where we're heading. So in the first, when we need to eliminate, we want to pick a strong base, and a very strong base such as OET negative or OME negative, but a strong base. And we do so, we eliminate, right, minus HBr, and we create the alkene in the most substituted position. In the next step, we want to add across an HBr, and that's just a simple addition. So the reagent itself, HBr, will produce the Markovnikov addition where the bromine went to the tertiary alkyl halide. The opposite could happen as well. Just again, choosing your reagents. If I had started with a big bulky base, we get a Hofmann elimination where the double bond is placed between the least substituted carbons. So the carbon 1, carbon 2 would create the Hofmann elimination. Between carbon 2 and carbon 3, you create the Zaitsev elimination. Here we see peroxide. And that peroxide lets you know that it's an anti-Markovnikov addition. So that HBr adds across, but in the anti-Markovnikov position, so it goes to the least substituted carbon, which would be the primary carbon, and we'd end up with a primary alkyl substrate. If we're using an alcohol, we have to modify that plan just slightly, and this is again emphasizing that before we can eliminate, before the leaving group leaves and eliminates, we have to convert the alcohol into a better leaving group. So if you're starting with an alcohol, you'll actually end up with a 3-step synthesis plan to move the alcohol from one position to the other. So here it's on a second number carbon number 2, and our last one we want it on carbon number 1. Before the hydroxyl group can leave, it's converted into an OTS, a tosylate. And remember, the tool for that is the tosylene chloride in a workup of pyridine. We use a strong, small base. Just remember that OME is another good choice. It doesn't have to be OET, but we're looking for a strong, small base to create the Zaitsev elimination. And you could work up with an acid catalyzed hydration. And that would produce an alcohol. I'm just trying to write that hydration. that you have the alcohol in the tertiary position, the most substituted. If we had done the same first step, we have to put in the tosylene chloride with pyridine to turn the alcohol into a better leaving group, but we used a big bulky base on this secondary alkyl halide. We produced the Hoffman alkene, where the double bond is between the least substituted carbon. And here I'm recognizing the boron in a peroxide workup, and I have to know that that is an anti-Markovnikov addition. So the alcohol moved to the primary position and not the tertiary position as above. So careful selection of the reagents allows us to kind of plan our synthesis. If we need to change the position of a double bond, let's say the double bond is in the cyclic structure between carbon 1 and carbon 2, we can add across the double bond, adding HBr. This would put the bromine on the most substituted carbon, followed by an elimination, where the elimination then can be placed between the methyl group hanging out and the carbon that's in the ring. How could we accomplish that? Again, adding HBr, we could see how we created the bromine on the least substituted carbon, but then the selection of the elimination is critical. A big bulky base turns that tertiary alkyl halide into the least substituted alkene. If I had treated HBr in the presence of peroxide, as the previous slide had us do, notice that the bromine added to the least substituted carbon. So this position with a peroxide and then a big bulky base would create the double bond and just move it between carbon 1 and 2 to originally carbon 2 and 3. So emphasizing the selection of your reagents to accomplish the task at hand. If you need to convert an alkane into an alkene, we looked at this slide earlier and said, well, we can use Lindlar's catalyst, and this will turn it into a cis configuration. We can use elemental sodium, and this will convert it into a trans configuration. Looking at hydrogen in a workup of a metal catalyst will saturate all pi bonds. You will always end up with the alkane in a hydrogen catalyst. And we went back this way. Now we understand how to go from the alkane sp3 to an sp2 using chapter 10, the radical mechanism. This is a radical mechanism to turn an ane back into an ene, and you can do a workup here where bromine and carbon tetrachloride adds across the double bond. So here after step 1, you'd have a bromine, and you add it again. You could keep adding bromine to all sides. The sodium amide then is going to kick out the bromine, and that bond collapses, and you end up back with the ine, a triple bond. Remember, we talked about how water is just added as the last step to make sure that you eliminate the negative charges at the end of the carbon alkyne group, and you end up protonating them with that water workup. Okay. So again, so much to review as we begin thinking about synthesis as a way to transform one into the other. Let's just practice a few, and you'll hear me think out loud. Propose an efficient synthesis for the following transformation. So again, let's just get our bearings and count how many carbons you see in the chain. I see a 5-carbon chain. I see a double bond between carbon 2 and carbon 3. So that's a functionality, a double bond. And there's an ethyl group at carbon 3. What do we have over here? I see that I still have the same length of the carbon, and the methyl group didn't change. It's still at carbon 3, but the functionality has changed. At carbon 1, we now have a bromine. So I see that we eliminated the double bond, and we added a bromine to carbon 1. So that's kind of what I've noticed here is how do we do that now? Let's kind of think through. It has the functional group changed identity, yes. And has it changed position? Yes. Carbon 2, carbon 3 has a functionality. It has a double bond. It's gone in the product. The bromine is not present at the beginning. At carbon number 1, it's present at the end. So we're just trying to get an idea of what we need to accomplish with our synthesis. We need to move the pi bond to the end of the chain. Now remember, that's got to be an anti-Markovnikov addition. So in our first step, an addition, remember the 2 steps, addition followed by elimination. I had to let my dog out. There we go. So the addition followed by elimination. I need to select an addition reagent that will add across the double bond to create the anti-Markovnikov addition. I don't want it to land on the most substituted carbon. I want it to land on the least substituted carbon so that when we eliminate the HBr, it goes to the carbon 1 to carbon 2 least substituted addition there. So we've got to plan what reagents are going to accomplish that. And so consider the first conversion using HBr in the presence of an alkyl peroxide. This will work fine in creating the secondary anti-Markovnikov addition. But we also have learned a second choice, and the second choice is boron oxidation, right? So with BH3THF followed by a peroxide, this is known as an oxidation, hydroboration oxidation. So with one choice, we create a secondary bromine, and in the other choice, we create a secondary alcohol. Both work, but let's think about what might be the better choice. HBr with peroxide, I can see like a one-step mechanism. Hydroboration and oxidation also is the anti-Markovnikov, but now I have an alcohol that's produced. And before I can go on, I'll need to put a next step in, because the next step is going to be elimination. To eliminate a hydroxyl group, I've got to convert that into a tosylate group in a workup of pyridine. So if I choose this step, it will work, but it's adding more steps to the overall synthesis. Before I can proceed, I've got to do a next step and convert hydroxyl into an OTS group so that then I can get the alcohol to leave in the elimination. So as we look at this, our original reactant, whoops, that popped down. The original reactant was between carbon 2 and 3. In the elimination process, as we're looking here, I want to have a Hofmann elimination occur. We had decided that there were 2 methods for the addition process. One of those is the HBr in an alkyl peroxide, creating a secondary bromine. And the other is using a boron compound in the presence of peroxide, known as oxidation. We can create the alcohol. Then I mentioned we have to add a pyridine step to change the leaving group, and then the base, the big bulky base of butyroxide, could eliminate in the Hofmann position. So remember, this is a secondary. We don't want a strong base here. If we had a strong base, we'd end up with the double bond in this position. We want it at the end of the chain, so we use a big bulky base. Now, which one of these, and they both accomplish the same thing. And this is, again, just the elimination step, right? We got to do the addition next. But at this point, the elimination step, I like this one, the top. Because one of the things as an organic chemist becomes better and better is trying to decide what is the most proficient or efficient, the least number of steps involved in getting from reactant to product. And if I can eliminate an extra step, I'm going to do so by selecting different reagents. So I like this one. We're going to go top. Add HBr, ROOR, and you've got that addition reaction. You added HBr in the anti-Markovnikov position. In the next step, you remove the Br by using a big bulky base, and you create the alkene in the least substituted position. We're ready for the last addition step to add the bromine back to position 1, because this was our desired product at the very end. Adding HBr in the presence of alkyl peroxide again puts it back onto carbon 1. So putting it all together, we could find this transition of changing a double bond from carbon 2 to carbon 3 into an alkyl halide at carbon 1 in only 3 steps of our synthesis. If we had gone the other way and created an alcohol, it ended up to take 5 steps to do the same thing. So the first is more efficient. Even though 2 plausible routes exist, we would select the least number of steps to accomplish it. So as we begin kind of taking next steps, we talked about, did the functional group change in section 2, and how do we accomplish changing one functional group to the next? Another consideration is figuring out if reactions change the number of carbons in the backbone skeleton. This makes us go back to section 9.10, the alkyne chapter, the alkylation of a terminal alkyne, increasing the size of the carbon chain. So this goes back to where we learned that carbon at the end of a triple bond has a very acidic hydrogen. And the acidic hydrogen can be eliminated, well, let's say by an amide ion. And it's a proton transfer, right? It's just plucking that off. And what's eliminated here then, we call this the carb anion. And this can be used as the next step in the reaction where this negative ion can reach out for that electrophilic carbon. The leaving group then leaves, and you've added on the length of that chain. So the alkyl halide, and I recommended using, like, let X equal iodine, because iodine is a very good leaving group with its large polarizable cloud. However many carbons you want to add on to the triple bond, just selecting if you need to go from 4 carbons to a total of 7 carbons, then I'm going to add 3 more carbons, make an iodine at the end because it's a good leaving group. And so the original 4-carbon alkyne has been lengthened with 3 more carbons by the careful selection of your substrate. And that's just a reminder from chapter 9, section 10. If you need to increase the number of carbons, this is really the only tool that we know so far in how to do that. If the size of the carbon chain decreases, then we have to go back and review chapter 8 and in chapter 9, the process of ozonolysis, taking an ozone and cleaving the bond. So here we have a 5-carbon chain. Well, I'll number it this way: 1, 2, 3, 4, 5. And the bond is going to break in the presence of ozone and a workup of DMS, a nonpolar solvent. And when that bond cleaves, here we've had an aldehyde. Notice that we're just increasing the number of C to O bonds in oxidation. I'll just write that. Increases the number of CO bonds. So here, this carbon, when it's cleaved, I end up with a double bond to an oxygen. And this carbon also to a double bond oxygen. So if I think about this, just kind of help me, when I see ozone, cut that bond in half, and wherever there was a carbon attached to another carbon by a double bond, that carbon will now just attach to an oxygen instead. So good sections to review here: 8.12 for alkenes. Take the double bond, cut it in half. The carbon is still in a double bond, but it's now leading to oxygens. So here are those 3 blue carbons leading to a, this is a carbonyl, C double bond O. And then I have 1, 2, 3, 4 more carbons The carbon that was in a double bond still is. It's just leading to an oxygen now. And remember, this also showed us that if we cleave the double bond here, you're actually just going to break the chain. So just kind of numbering, here's the carbons that were in the double bond. Here's the carbons that were in the double bond. And that's the methyl group down here at the end. So 1, 2, 3, 4, 5, 6, 7 total carbons. And at carbon 2 and 7, you see the C double bond O. And the other section I'll have you go back and review is section 9 for the ozonolysis of alkynes. So here's the triple bond, and as this cleaves, it forms carboxylic acids. And those are what I always say, COOH. The carbon in an alkyne is even more oxidized because there's more pi bonds there. So we add a carbonyl carbon as well as the hydroxy, COOH. If you cut a carbon here, cleave the bond, and you're left as a terminal, CH, this will form carbon dioxide as well as the carboxylic acid. And those were notes that you took back in that section when we covered chapter 9, section 9, ozonolysis of alkynes, oxidation, increasing the number of CO bonds. So we found a way to lengthen a chain. We found a way to break a chain, right? Lengthen the chain means add more carbon. Reduce the number of carbon. Think about ozone. Identify the reagents that can be used to achieve the following transformation. So let's just practice this skill. We see a cyclohexane, and at carbon number 1, we see another carbon leading out to a bromine. Now the cyclohexane hasn't changed. I still have one more, the original carbon, but it looks like we've added on 2 more carbons in a triple bond. So 7 carbons total turned into 9 carbon total. All right, so that's something that our goal is to increase the length of the bond. Now, think of this as your substrate. And this guy here is the acetylene, the YNE, that negative ion, the carb anion that we want to add on to lengthen the chain. And so as we think of this strategy, it really is just a one-step mechanism. Here are the 2 carbons we want to add on in a triple bond. We want this to be the negative ion. This is going to reach out for the electrophilic carbon. The leaving group leaves, and so yes, over here would also be a bromide. The leaving group left, and we've added on the carbon chain. So a simple reminder of how we can take the acetylene ion and use it to lengthen a carbon chain, and we'll end up with that triple bond. Let's kind of pause our lesson here. We've got a great start, and I'm going to encourage you to do as many practices as you can through your Wiley homework, your skill builders. Do as many as you can from the first 3 sections, and I'll come back in a much shorter video and try to give you some tips on how to approach synthesis problems.